Hi everyone. Now that we know the definition of vapor pressure, we are going to look at really the relationships of vapor pressure among three different things. In this lesson, we're going to look at temperature versus vapor pressure. We're going to look at boiling point versus vapor pressure. And then finally, intermolecular forces compared to vapor pressure as well. So the first relationship we're going to look at is really temperature versus vapor pressure. And in order to understand that, we want to look at two identical, beakers or setups. And these two setups are going to be in closed systems. So each of these beakers is going to receive a lid. We don't want things lost to our surroundings. We want to keep everything inside. And to keep everything else the same, we're going to deal with liquid X. So both of these beakers are filled with liquid X. Now, since we're looking at the relationship of temperature, we want to change the temperature somehow. And the best way to do that is put it either under fire or put it under ice. So let's look at the left side first. Now, on the left-hand side, by putting it under a flame or putting it under a Bunsen burner, we now raise the temperature to about 120 degrees Celsius. We're forcing the liquid to become hotter because it's receiving some heat energy. Now, what happens at this point is that we already know it's at a higher temperature. By placing it under a Bunsen burner, we can naturally see that the temperature is going to get higher. What we should remember that as this extra heat energy is being applied to the beaker is that the kinetic energy or the energy of motion starts to increase. We're making the liquid particles move faster and faster and faster. Now, as the particles move faster, what now occurs, which we talked about in the last lesson, is that on the surface of the liquid, we're going to have more evaporation. Because the particles are moving faster. So if we were to draw an image of that, say the surface liquid has a couple particles, but we're going to see a lot more evaporated vapor above the surface of the liquid. So as we see more evaporation, we see more vapor. Now, what naturally is going to occur is that as we have more vapor, each of the vapor particles is going to push on the container, push on the liquid. And that push is really that vapor pressure. So every little one of those particles is going to increase the vapor pressure or the total vapor pressure. And that's because there just happens to be so much vapor above the surface of the liquid. Now, on our right-hand side, the same identical beaker, closed system, liquid X, is now going to be at a temperature at 10 degrees Celsius because we're going to put some ice cubes underneath it. So it's going to be at a lower temperature. And we want to manipulate temperature just so we can see the relationship. As we lower the temperature, we tend to see the kinetic energy or the energy of motion decrease. The particles are moving very slow compared to the beaker on the left. And as the particles tend to move slower, what we're going to see is we're going to have less evaporation. And if I were to draw that in the image, we're going to see a lot more liquid particles on the surface than we are vapor particles. So naturally, less evaporation means less vapor particles. each of those vapor particles exhibits or pushes on the container and on the surface of the liquid. So as we have less vapor particles, we're going to also see a decrease in vapor pressure. So by setting up these two examples and putting one under a Bunsen burner and putting one on ice, we tend to see that the relationship really is that as we increase our temperature, we're going to also increase our vapor pressure. And that's the first relationship that you have to remember. At higher temperatures, we're going to have more vapor and we're going to have a higher vapor pressure. Whoops. All right, now the next thing, boiling point and vapor pressure. Same idea. These beakers are going to be in a closed system, so they need to have a physical barrier, and that's going to be our lid on the surface. But now I want to manipulate something else other than temperature. So on the left-hand side, what I'm going to have is I'm going to have my regular liquid X. Perfectly fine. And liquid X has a boiling point specifically of 100 degrees Celsius. On the right-hand side, I'm going to now have a different liquid. I'm going to have liquid Y. I need to manipulate the nature of the particles, or the nature of the liquid. And this liquid Y now has a boiling point of 60 degrees Celsius. Now that I have this setup, we're going to say that the room temperature of the room is now at 65 degrees Celsius. So what we're essentially saying is that both these beakers, even though they're filled with different liquids, are going to be at the same temperature of 65 degrees Celsius. Now that's important because each of these liquids has a different boiling point. So let's take a look at the beaker on the left-hand side first. On the left-hand side, we see that it has a higher boiling point than the beaker on the right-hand side. That part's easy to see. Whoops, I forgot the word boiling point. The liquid on the left, or liquid X, has a boiling point of 100 degrees Celsius, but liquid Y has a boiling point of 60 degrees Celsius. Since the boiling point is at 100 degrees Celsius and the room is only at 65 degrees Celsius, we tend to see less vapor particles. And that's because the boiling point is so high. It's set higher than the actual temperature. So in this situation, if I were to draw the particles, if I could see inside the liquid, I'm going to have definitely more liquid than I am vapor. Now, the less vapor that hangs above the liquid, we're going to see that it has a lower vapor pressure. Now, let's switch to the right-hand side. We'll notice that in liquid Y, the boiling point is at 6 degrees Celsius. Sorry, 60 degrees Celsius. So it has a lower boiling point than the beaker on the left-hand side. However, since the room temperature is at 65 degrees Celsius, which is higher than liquid Y's boiling point, we're actually going to see more vapor particles. And we see that because the room temperature is above our boiling point. So this liquid actually can be boiling. So we might have two liquid particles, but we're going to have a lot of vapor above the surface of the liquid. Now, as there are more vapor particles, we're going to have a higher vapor pressure. By looking at these two beakers side by side, we actually are able to see the relationship between boiling point and vapor pressure. We see that higher boiling points give us lower vapor pressure, and a lower boiling point will give us a higher vapor pressure. So it's important to know that relationship between boiling point and vapor pressure. Now, our last relationship has to deal with intermolecular forces and vapor pressure. The beakers are the same, once again, going to be a closed system. And we're going to have different liquids again. Well, this is going to be liquid B. I'm just going to put a little B here. And on the right-hand side, let's have liquid C. Now, liquid B, someone would have to tell you, has a weak intermolecular force holding the liquid together. And when it has a weak intermolecular force, what that means is that the liquid easily changes into a gas. We tend to see actually this setup. And that's because we don't have to break the intermolecular forces in the liquid for the particles to become a vapor. Now, when this liquid has a weak intermolecular force, we tend to see more vapor particles. And once again, once we know that there are more vapor particles, we're always going to have a higher vapor pressure. On the right-hand side, our liquid C, and someone would have to tell you this, has very strong intermolecular forces. When the liquid has very strong intermolecular forces, it means that the liquid wants to stay a liquid. It's almost like the intermolecular force acts like a glue. It says, okay, you stay in this phase until you can receive enough energy to break the intermolecular force and then also break free out of the liquid. So in this case, when a liquid has a very strong intermolecular force, you tend to see a lot of the particles stay a liquid and very few particles above. So we're going to have less vapor pressure. First we're going to have less vapor above the surface because we have to break the intermolecular force and then give these particles enough kinetic energy to become a vapor. And when we have less vapor particles, naturally, it's going to have a lower vapor pressure. So the relationship between intermolecular forces and also vapor pressure is really when you have a very weak intermolecular force, you're going to have a very high vapor pressure. And when you have a very strong intermolecular force, you're going to have a very low vapor pressure. Okay, that's it for now. I'll see you in the next lesson.